In this video, we're gonna move on to the implementation of the analytical intersection solution that we've derived, the plane equation and the sphere equation. So I've created a new shader with the exact same code from the camera model. So the first thing I'm gonna do is just to create a new color vector that's gonna be completely black. I want to get rid of this cube map since we're already done with it. Alright, now we're going to try to render a sphere and a plane in as a 3D image on the 2D screen. Alright, so let's kind of plan this out. Right, let's plan the scene that we're going to have. So both our geometries are going to be centered at the origin. So there will be a plane here and there will be a sphere. It's almost like a half sphere because half of it is clipped under the ground and light really can't really penetrate the ground. So this will be what we're seeing, and right now the camera is kind of embedded in the plane and looking through the plane. That's no good. So the first thing we're going to do is to find a suitable position for our camera. Right now our camera is 3 units behind the sphere where the center is, and we can just move it up by 2. I think that's pretty reasonable. Actually, let's move it up by 1 so that we can get a so that most of our screen is not filled up by the plane. Otherwise, it would be looking straight down. Right? There's not much to see except the plane. So what do we do? Let's just first write the intersect routine. What this is going to do is that given the ray origin, given the ray direction, we return the parametric t value that will map to the intersection point. Well, what if this our array does not intersect with anything? Well, we can define a t max term that's really far away, right? Let's just return. Yeah, we can define a t max term that's really far away, so that when we can assign t max to the initial t. We know no geometry is going to be that much far away, so that if we initially assign it to t and it goes through some kind of runs through our intersection code, and if there's no intersection, then we never assign anything to t and we just return t. If we detect that the return t is equal to t max, then we know it did not intersect with anything. So the t intersection result is only valid if it's bigger than 0 or it's less than t max, which is the maximum distance that we're. Alright, so look at the plane equation. Plane equation is very simple. It's just t equals negative dot ray origin dot normal over ray direction dot normal. Remember what I said about the denominator, I have to be careful with that. So let's first define the plane normal, which is the characteristic that we require to the intersection. Oops, it's vec3. And the denominator is rd dot n, so denom. Let's just put a bracket so that we don't share the same namespace as the sphere intersection routine. Since we know both intersections are going to happen here. So t is the denominator is going to be equal to dot ray direction with the normal of the plane. And if the denominator is not equal to 0, which means that the ray is not completely parallel with the plane, there is a chance that this might intersect, right? So we can move on and compute the plane t. So this is t if it ever intersects with the plane. So that is negative dot ray origin dot with n and divided by the denominator. If plane t is, like I said, bigger than 0, so if it's positive, and plane t is less than our existing t, So that is, if we had a previous intersection, we only update t if the current intersection is closer than the previous intersection. Because what we want to do is, if we move along some geometry, there's multiple stuff that's in the way, we want to get the intersection point as the closest to the camera origin, because that's where the light is first going to be hid on the geometry. That's where the light primarily comes from. So only update it if the current intersection t is less than the previous one. If this is the case, then we update t, we plane t, r0, our origin, and normal is plane normal. All right. So this intersection routine now, it does intersection test with ray and the plane, and plane is overlapping with the origin with the normal pointing straight up. So what we do is we call this function to find the intersection t, intersect ray origin, ray direction. So if t is positive and t is less than t max, that means we've hit something. At the top, if this ray successfully hit the plane, let's just assign it to white. But right now we don't see anything. It's probably because it's bugged. All right. So let's see. Dot denominator. If denom not equals to 0, then we update it. Okay. I don't really see what the problem is. Let's look at the equation again. So RD. Okay. And if the return t is less than t max and t is bigger than 0, 0, that means we've hit something. What happens if I move this away? Did that? Okay, we're in a bit of a weird situation. So apparently plane t. Oh, right. I forgot. I said I was going to move up the camera by 2, but I didn't do that. Okay. So ray origin, move it up by 2, and move it back by -3. 2 obviously is a bit too much, so we only move up by 1. You can kind of see this plane projection onto the 3 screen, right? Well, that's pretty cool. But there's no color. We can't really tell it's really working correctly because there's no any complexity on the graphics. The detail is literally just flat. What we're gonna do is we're gonna add the sphere that will be embedded in the plane, which looks like this. This is what we'll be expecting. So this is, let me just put this in here. This is the plane intersection, and now I'm about to begin the sphere intersection. Again, the parameter for sphere is r, the radius. We want it to be, do we assign a radius to the sphere? No, we didn't. So if we're 3 units behind the origin, we might want to assign 1 to the size of the sphere. That's the reasonable size, radius. So we know the radius, right? The equation. First of all, what we have to watch out for is this term inside the square root. So let's first compute the square root term without actually square rooting it, because if it's negative, then something bad is going to happen. So here's the power function in GLSL. Again, if you don't understand what's going on, I advise you to look up the GLSL spec. So ray origin dot with ray direction powered by 2. Subtract minus 4.0 times the dot ray direction with itself, the dot ray origin with itself, minus r squared, which is just r times r. The sphere, the ray will only intersect with the sphere if the square root term, this term inside the square root is going to be positive or 0. If it does not, then that means there is no root for this function, meaning that there's no intersection at all. So if the square root term is bigger or equal to 0, then we continue our computation. So sphere t is -2. Let's just, it's going to be in a fraction form, so let's just do this, and dot right direction plus, right, there are two terms. I mean, there are two roots for the sphere intersection solution. Why is that? It should be really obvious, because if the ray intersects a sphere, obviously there's going to be an entrance point and there's an exit point. There's going to be two roots to our solution. There's two T1 and T2, at which positions that the ray intersects with the sphere. What we want, like I said before, is the earliest termination point of the ray. So it will be, we'll just be taking the minimum, function of t. Why am I using mouse? I don't know. So something like this. That is if the t is positive, because if one of the t is negative, then finding the minimum will return. Again, there's something we don't have to worry about, since our camera will be constantly outside of the sphere, and so both of them, if they intersect at all, they're both going to be positive. So square root, we'll have the square root term inside the square root, right? And the denominator, I believe, is just 2 times ray direction dot itself. This compiles, and sphere t is the new t we've computed. We only update t to our new sphere t if sphere t is, bigger than 0 and it's an earlier termination than the t we currently have. Only update t when it's, when the situation is like this. So t equals sphere t if this is true. Right. However, we kind of have no way to tell if this works or not, because we have no way of distinguishing which, what the material is that we hit on a circle. We only know the distance, but it doesn't help with the screen shading. So what we're going to do is to do a basic material differentiation for the intersection routine. Like, when the ray hits some object, we also store information about what's the material of the object that I just hit. So that will be helpful when we, differentiate materials, and we can write different colors for sphere and the plane, so that we can, actually visualize the image and know if it's working correctly. So remember the out keyword that I talked about. It's going to come in handy here. Out keyword, it just, when you write value to it, assigns some value to this argument. When the function exits, whatever code that's calling this function and fed the variable into this argument will have the value that you wrote it to inside this current function. So matID by default, I want it to be -1. -1 denoting that it hasn't hit anything yet, it's in the void. And if plane t, if it hits the plane, then I return 0 as the material index. By the way, matID here stands for material index. Material index is -1, then that means there's no intersection at all. And if it has the sphere, then matID becomes 1. So the material index for the plane is going to be 0, and the material index for the sphere is going to be 1. Compile this doesn't work because we didn't put the arguments in here. So let me just make matID real quick. And after this intersection routine, matID will be filled with whatever value we'll write to in the end. Okay. So right now what we can do is check matID if the material index is equal to 0. So that will be the plane we want to output white. If it's not, then we output red for the sphere. Doesn't work. Well, obviously. I said that there will be two roots for the sphere intersection, and I totally forgot about that myself. So if you look at the equation again, this operator, this is both addition and subtraction. So we need two roots, so basically two scalars, sphere T1 and T2. And one of them, these roots have to be negative, right? then we get whatever the minimum is when you're comparing these two t's. So sphere t would just be the minimum of sphere t1 and sphere t2. There you go. That looks reasonable. It's a reasonable image to have if the sphere is actually 3D, because you can see there's a curve here. It's you can infer this it's a cross section of a circle with the plane, right? So let me just make the plane some other color, not white. It's kind of weird. Whatever. No, not 0, white. So that is it. It's the implementation of analytical ray intersection for plane and sphere. And this is the code for it. All right. Thank you for watching. I will see you next time.